Okay, we are going to take a look first at the Rube Goldberg device. So this reads, the problem reads like this. It says, a Rube Goldberg device is a series of items set up in such a way that it takes an extended period of time to perform a simple task. Some are pretty cool. We will focus on one portion of a Rube Goldberg device in which a boot is attached to a broomstick on a pivot at a height of 1.2 meters above the surface. Here is the diagram. It says the boot is released and strikes a ball. So for part one, this one, everybody should be able to get pretty easily. It says calculate the maximum speed of the boot achievable when the height is 1.2 meters. So we remember that our potential energy at the top is going to be equal to our kinetic energy at the bottom. And if we break that equation down, that's mgh is equal to 1/2 mv squared. The only thing that we have right now is the height, and you might be thinking to yourself, well, we don't know the mass of the boot, but that doesn't matter because mass shows up on either side of the equation here and here, so we can make that go away. Bye. So that leaves us with gh is equal to 1/2 v squared. Our value for g is 9.8. Our height is 1.2. It's a multiplication problem, and that's going to be equal to 1/2 v squared. Let's hammer that out on the calculator. 9.8 times 1.2 is 11.76, and that's equal to 1/2 v squared. We're going to divide, you can either multiply both sides by 2 or divide by 1/2, it's up to you. I'm just going to multiply by 2. That gives us 23.52 is equal to v squared. Square root of both sides. And we get a max velocity of 4.84, well, 4.85. Round up, meters per second. Technically speaking, we should leave that as 4.9 or round up if we want to do sig figs, because we have 2 sig figs here. So let's just round that up to 4.9. All right, so far so good. So it says, explain how increasing the deformation of the boot could increase the speed at which the ball launches from the boot. Well, if we look at this in terms of impulse, and we look at our impulse equation, F delta T equals M delta V, which is equal to velocity final minus velocity initial. If we increase the time, or if we increase the deformation, the smushiness, we're going to increase the time that it's in contact. So by doing that, that's going to increase the overall impulse value. So now our overall impulse will increase. So we get an increase in impulse, which means that when we break that down and try to equate it to the other side of the equation, your mass isn't going to change. Your final velocity is really the only thing that can change, because if you remember, that initial velocity is 0. So with an increased impulse, the only way you can mathematically get that to work out on either side of the equation is by increasing this value right here. So that increases that final velocity value. All right, moving on. So it says, in a different arrangement, the boot is in contact with the ball for a time of 220 microseconds. So we have a time of 220 microseconds, which is equal to 220 times 10 to the minus 6 seconds. Don't forget, we got to convert that. The boot has a mass of 0.17 kilograms. The ball has a mass of 45 grams, so divide by 1,000, 0.045 kilograms. At the moment of contact, the ball is at rest, so V initial for the ball, or we would call it U if we were using IB nomenclature. The ball's at rest, so that's a 0. And the boot is moving with a speed of, so velocity initial for the boot is 38 meters per second. The ball moves off with an initial speed of 63 meters per second. So our final velocity of the ball at that moment is 63 meters per second. So it says calculate the average force acting on the ball while the boot is in contact with the ball. So if it's talking about velocities and masses and times, that should be your indicator that it's an impulse problem. Now we're talking about the force acting on the ball. So because we're talking about the force acting on the ball, we're going to use ball numbers to calculate the impulse. So force F delta T is equal to M times VF minus VI, or V minus U if you're using IB terminology. So that means it's going to be F times 220 times 10 to the minus 6, and we're going to set that equal to the mass of the golf ball, because remember we have to use golf ball numbers, 0.045 times our final velocity, 63, minus our initial 0, and solve for F. So when we do that, we're going to just divide this entire thing by 220 times 10 to the minus 6. So 0.045 times 63 divided by 220 times 10 to the minus 6 gives us a force of 12886 newtons. And if we want to do this in sig figs, if you guys notice, everything's all 2, 2, 2, 2, 2. So we got to slide this into scientific notation, which would give us a force of 1.3 times 10 to the 4th newtons, if we're answering in sig figs. And we got to start getting back to that, just in case. I don't want you guys to lose silly points on the exam if we can avoid it. So for the test, I prefer you guys answer with sig figs. If you don't answer with sig figs, I'm not going to take any points off, but I will kind of write you a little warning. So it says state the average force of acting on the boot while it is in contact with the ball. Well, this one's actually pretty simple, especially because here, this is kind of your clue. It says state it. So if it says state it, it means that you don't have any calculations required. So if we have, this is ball, this is force acting on the ball. So ball acting on boot. If Newton's third law says every action has equal and opposite, or forces act in pairs. So that means that the force would be equal and opposite, which would be negative 1.3 times 10 to the 4th newtons. Bam. Okay, and the last section is pretty straightforward. It says calculate the speed of the ball at the instant it loses contact with the ball. So this is a column problem. So we've got our momentum of the boot. We have our momentum of the ball, and that's all before. Then we have our P prime boot and our P prime ball. So that's everything after. Remembering conservation of momentum, your total momentum before is going to be equal to your total momentum after. So we got a mass of 0.17. We have a velocity of 38. I pre-worked out these numbers for you guys. So your momentum here is 6.46. Your ball has a mass of 0.045. Velocity is 0, so we can make this whole section go away. Bye. And then our P prime boot is, our mass of our boot is 0.17. Our velocity final of this boot is going to be, we don't know, that's our X value. And then we have our mass of the ball, 0.045, velocity of the ball, 63. Mass times velocity, in this case, is 2.835. So setting that up in an equation, we have 6.46 plus 0. That's everything on this half, setting equal to everything after. 0.17 times x is 0.17x, and 0.045 times 63 gives us 2.835. I'm going to move this whole equation down here, up over here, so that I can work it. So 6.46 is equal to 0.17x plus 2.835. Subtract from both sides. That gives us 3.625 is being equal to 0.17x. Divide both sides by 0.17. And our x value is going to be equal to 21.32 meters per second. Doing it with sig figs, that just rounds back down to 21 meters per second. Bam. Done. Rube Goldberg device, ladies and gentlemen. That's that.